Other questions about anything? Well, at the end of last hour, I was talking about some of my favorite things. I was mentioning that this problem, if you have polynomial data on the unit circle, so that'd be a polynomial, real polynomial in x and y. So that's all the coefficients would be real, etc. Then the solution to the Dirichlet problem with that polynomial data is also a polynomial. It could be a different polynomial. In fact, it's a harmonic polynomial. So you start out with a polynomial that p wouldn't be harmonic, but you can get a harmonic polynomial that has the same boundary values. And a very simple way to do it on the unit disk is to replace x by z plus z bar over 2 and y by the corresponding thing, and put it in there and multiply it out in the polynomial definition. And then you get a polynomial in z and z bar. And when you combine all the coefficients with that 2i there, some of those numbers are going to be complex numbers. And that's okay. And then you look at each one of those little pieces and you realize, aha, I know how to extend those harmonically because there's the three cases. Z to the n times w bar, z bar to the m. When n and m are equal, then of course that's 1 on the boundary. And 1 has a harmonic extension as itself. And then when n is bigger than m, I showed you last time that that would agree with z to the n minus m on the boundary. And of course, the real and imaginary parts of that are harmonic. And so similarly with the last case, when m is the big one, then it's z bar to the m minus n on the unit circle. Because z times z bar is 1 on the unit circle. That's why. And so you can extend those harmonically, and you realize, oh, I've got this real polynomial, p of xy, and it's equal to the real part of when I add those all up and put the coefficients in there, I get two polynomials. I'll put the constant thing in with the z terms and get a q1 of z, and then the other terms would be z bar terms. That'd be a q2 of z. That's a polynomial. They'd have complex coefficients. But when I think about the real part of that polynomial and write it like that, it agrees with my data on the boundary. But that thing on the right is a harmonic function. And it's a polynomial in x and y. So I get a harmonic polynomial that solves the Dirichlet problem that way. Of course, it's very special to the disk. It's also possible to show that ellipses satisfy this property. That's a more fun, fancier thing to show. It's really fun and really elementary, and it just uses a fact from linear algebra in my favorite proof. Sometimes I teach it because I just like it so much. I think I'll save time and not do it, unless you're dying to see it. By the way, if I took the imaginary part of that thing instead of the real part, that imaginary part is 0 on the boundary. Because, when I started out here, when I started out, that p of xy, when I put in complex numbers, the resulting thing on the right would have the real part is the right thing, but the imaginary part would also be the right thing, which is 0. So the imaginary part of that complex polynomial is identically 0 on the unit circle. I guess it's identically 0, period. We care about it on the unit circle where it's also identically 0. And so that solution down here that I get, if I take the imaginary part, that's a harmonic function that's identically 0 on the boundary. And so by the maximum principle, it would be identically 0, period. Interesting thing to note. So this is an example where you understand something better by going into the complex domain and then going back into the real domain and taking real parts. That's sort of a classic motivation for why we study complex analysis. We gain insight into real problems that way. Well, the Robinson-Shapiro conjecture is that disks and ellipses are the only domains with this property, that polynomial data has polynomial solutions to the Dirichlet problem. And that's an open conjecture. Seems really hard. Well, I don't know if it seems hard. I expect the proof someday is going to be easy, because I only look for easy proofs. And I might find it someday. And it's a fun fact that disks also have the property that if the boundary data is a rational function in x and y, then you can play similar games that are fun and show that you get solutions which are harmonic functions which are rational in x and y. They have singularities, but the singularities, they would be, if they have any singularities, those singularities would be outside the unit disk. They're rational on the inside and nice and smooth on the inside. Disks have that property, and in this case, ellipses do not have that property. And the most fun I ever had doing math research, I wrote a paper with 4 people, me, Dmitry Robinson, and Harold Shapiro, and Peter Ebenfeld. And we were able to show that only disks have this property, that rational data goes to rational solutions. And so the Robinson-Shapiro conjecture is open, but the same conjecture for rational functions has a solution. It turned out not to be too hard. It was the most fun I ever had doing research with anybody. And we never met in person. We communicated by email mostly. It was something. Questions about that?
What made it fun?
Well, these guys are fun. Shapiro was a scream. You know what it is to lift in topology, to lift a mapping? He said he didn't do any heavy lifting, for example. But Robinson loved to do some heavy lifting, so that kind of fun. Well, today I'm going to talk about the weak averaging property, which turns out to be simplify certain things in a major way. But before I get to it, there's a theorem I should mention. Okay, so this is just for fun. Now we're back to the course material. If a sequence of harmonic functions converges uniformly on compacts, so a sequence un of harmonic functions, real valued, on a domain omega, converges uniformly on compact subsets to U on omega. Let's see, I want to say omega. Omega is a domain. On omega. Then, of course, the limit oh no, okay, so furthermore, derivatives. All partial derivatives. So if I took dn plus m, dx to the n, dy to the m of uk would converge uniformly on compacts to the corresponding derivative of u. And, we've gone through proofs like this when it comes to analytic functions on omega. So the proof, I guess I'll mention what I said last time. before the disaster. In Math 504, we know that uniform limits of continuous functions are continuous. So U is continuous on omega. And the averaging property, so an easy thing to see, the averaging property for the UNs implies the limit has the averaging property. And of course that would imply we got a continuous function with the averaging property. The big theorem last time was that U is harmonic. So no work. And of course it's by uniform continuity, by uniform convergence. So the integral from 0 to 2 pi of U of a z naught plus r e to the I theta d theta, that would be equal to the limit of the same integral with the uk there as k goes to infinity. And by uniform, and that circle is a compact set. The circle radius r about z naught is a compact set, and we have uniform convergence on that compact set. So this would tend to the integral ... with u in it. What am I saying? Yes, I'm sorry. So this, and here we're using by uniform convergence on a compact circle. That would be CR Z naught, which is compact. And of course, these satisfy the averaging property, so that would be the limit of uk of z naught, which converges uniformly to u of z naught. Check. So that's all there is to it. And to see the derivative part, we have the Poisson integral formula. And that Poisson integral formula is a very nice kernel that you can differentiate under the Poisson integral in the Poisson formula. Like we did with the Cauchy integral formula. Remember, we differentiated it, and we could see that the derivatives converge uniformly on compact sets. You do the same thing with the Poisson integral formula, and then, of course, you're going to restrict to smaller disks with the standard tricks, cover by disks. Well, you shrink the disks, and you cover by shrunken disks. Like we did, and get a finite cover when you're dealing with with compact sets, subcover, etc. It all works exactly the same as we did with the Cauchy integral formula. You just have to know that you can differentiate under the integral sign. But you look at the Poisson kernel, it doesn't do anything bad, so there's nothing stopping you from doing that. And it's basic analysis to take a difference quotient and write it out, and to realize I can take the difference quotient under the integral sign, and then just show everything converges beautifully. That's how it works. So it's not hard. Okay, so that's a theorem we have now. Here's a remark that's worth thinking about. I mentioned there's this famous formula that P of z e to the I theta is equal to 1 over 2 pi times 1 minus mod z squared over z minus e to the I theta. A couple lectures ago I forgot to put the square right here when I wrote this. I fixed it when I posted the notes, but that square belongs there. And that's the real part of 1 over 2 pi z plus e to the I theta over z minus e to the I theta. And so the Poisson integral is equal to, so you, remember u is equal to the Poisson integral. I like to write the Poisson integral like this. And that's going to be equal to the real part of the integral 1 over 2 pi integral from 0 to 2 pi of this thing, z plus e to the I theta over z minus e to the I theta, u of e to the I theta. Let's be on the unit disk. Okay. Now I put a d theta. And I wish that was the contour integral. So I do my standard trick that I've done. I wish I had an I e to the I theta here. So I give it to myself. And then I realize, aha, when I give it to myself, I've got a dz. And so this thing is the real part of kind of like a Cauchy integral. Let's see, it would be the real part of 1 over 2 pi. Let's see, so the z, that first z one is going to come out. Well, why don't I write it like this? Integral around c1 of 0. I got to leave this as z, so I'm going to make the e to the I theta be a w over z minus w, u of w, dw. Then I've got that 1 over I e to the I theta. That's 1 over iw. Anyway, when I write that all out, it looks like the Cauchy integral formula. I would split it into two. First I have a z in the numerator there, this z right here. I can pull that out in front of the integral. So I'd get an integral that looks like a Cauchy integral of something. The w is just, and those functions are continuous and nice, and so I've got a Cauchy integral. And then the w part is another Cauchy integral with a continuous function up in the top. And so homework 2, problem 1, shows that this is, that's how I would differentiate under the integral, by the way. I can see that now. I could even use homework 2, problem 1 to see that. But a fascinating thing, okay, so this looks a lot like a Cauchy integral. Homework 2, problem 1. That thing is analytic in Z. Okay. That's fascinating because that means if I take the imaginary part of that, I get a harmonic conjugate for harmonic U. So a fascinating thing if you take the imaginary part, then we see a u goes to a v, which is equal to a harmonic conjugate of u. And we have an integral transform that spits out a harmonic conjugate from the u. So I'm integrating with respect to u, and it spits me out a v. That turns out to be a fascinating operator. And we've seen in one of the homeworks that if I give you a continuous u up to the boundary, the harmonic conjugate doesn't even have to be bounded. So that's a weird operator, and it's delicate. So any questions you can ask get pretty weird pretty quick. And the fascinating thing is, if u is in L2 of the unit circle, then the harmonic conjugate is in L2 of the unit circle. And so that's a fascinating operator, and was one of the reasons people invented Hilbert space, and it's called the Hilbert transform. And it's very interesting. U can be continuous, so U continuous, V not continuous is possible. V not only not continuous, but not bounded. But it turns out that U is in L2 of the unit circle. Square integral implies V is in L2. And there's a bound. It's a bounded L2 operator. That's really interesting. And people have spent years and years studying those operators. Okay. Well, sorry for the slow start today. The main topic I was going to start with was the weak averaging property. And here's what it is. A continuous function, u, on a domain omega has the weak averaging property. Okay, so I'll call it WA prop. If for each point in the domain there exists a radius an r bigger than 0 such that let's see, we need the disk of radius r about a to be contained in omega, and we have the averaging property at least inside that disk. So we would have u of p, I guess I meant to call pa, for each point in omega, such that u of a is its average. On circles, at least are small enough to be radius less than r. So a plus rho e to the it dt for 0 less than rho less than r. And the thing to note here is that the radius radius r might be small. R could depend on A. R depends on A and could be considerably smaller than the distance to the boundary. The distance from A to the boundary of omega, or the complement of omega, whichever you prefer. Okay, well, the theorem is that the weak averaging property implies harmonic. So weak averaging property implies harmonic. And the proof we've already sort of done. There's just one little catch. So let's see. This is a local theorem. And so it means I can do my usual thing and restrict attention to a disk, and then I can change variables by z minus c naught over r radius, and think of my function on the unit disk. So we can reduce to I'll reduce to u continuous on a disk of radius capital R about 0, where R is bigger than 1. And U satisfies the weak averaging property. Inside that disk. Okay, let's see. So what's the standard trick? Standard trick is to take the Poisson integral. So we let u twiddle of z be the Poisson integral of the boundary values on the unit circle. So that'd be the integral from 0 to 2 pi p of z e to the I theta u of e to the I theta d theta. Well, u is continuous, so we know that that solves the Dirichlet problem. So we know that u twiddle equals u on the unit circle. And u is harmonic inside. U twiddle is harmonic in the unit disk. So of course I want to show that u twiddle equals u. And last time it was just the maximum principle, and it was fairly straightforward. And if you try to do that this time, remember we let that disk go out and touch the boundary? I can't do that this time because I've got the weak averaging property. So let's let u, capital U, be equal to u twiddle minus u. So, and let's let m be the max. On the closed unit disk of u. Well, let's suppose that max is positive. Well, if I start playing around thinking of my old proof, my issue is that I can't let that disk get bigger and bigger until it touches the boundary. And that's how I showed that I get this contradiction if that maximum was positive. And so if you think about it for a while, let's let K equals the set of Z in the closed unit disk such that U of Z is that max. We know that the circle is not in that set. So we know that C1, 0, is not in that compact set. And that's a compact. So we know it's not in. And in fact, so what do we know? More importantly, let me move this. Is this what I did last time to kill myself? Let's see, we know K is compact. That's just basic analysis topology. If I have a limit point in K, those are points where the continuous function is equal to the max. The limit of that limit point would also be in K by continuity. So it's a very easy thing to see that K is a compact set. So we know K is compact because it contains all its limit points. And we know that the unit circle, it's not in K, it doesn't intersect K. So in fact, K is a compact subset of the unit disk. So K is a compact subset of D1, 0. Okay, so let me draw my picture here. I need a radius. Modulus of Z is a continuous function on that compact set. So it attains its max. At a point, its max, let's call it Rm for R max. It attains its max Rm at a point Z naught in K. Okay, here's the picture now. Here's the unit disk. Here's K. Here's the point Z naught, where it assumes its maximum. That's the maximum rate, the maximum radius. Okay. And now I have the weak averaging property. So let's see. I need a dotted circle going around here. There's the Z naught. I have the averaging property on this circle here. It might be a small circle. But if you stare at that small circle for a second, so we have the averaging property. Okay, there's that small circle. But if you think about that, it's equal to m at Z naught, which is the max. And this part of the circle is strictly less than m on that part. So on that part of the circle, U is strictly, or U, capital U, is less than or equal to m. I mean, it's strictly less. So U is less than or equal to m, and it's strictly less than m on that red part of that circle that bulges out there. And so we get the contradiction by the usual maximum principle argument. Because the k is where it's equal to m, that's the max. And this z naught is the extremal point on that. And so that radius is finite. I mean, it's not 1. So that dotted circle is strictly inside the unit circle. And so when it bulges out there, that part of it is where the function is strictly less than m, because it's equal to m on the purple k. So u of z naught equals an average of stuff which is less than or equal to the max and strictly less than m on an interval, an open set. And of course that's the usual contradiction. So that m is less than or equal to 0. And we repeat, actually the m is equal to 0. And now we repeat the same argument again, except now we use u minus u twiddle. Of u twiddle minus u, and we get that u is equal to this Poisson extension, and of course this one is harmonic. On D10. So that's clever.
So I'm a little confused. What exactly were you contradicting? I don't remember what we
I assumed that m was positive, and then I get this thing that can't possibly be true. Okay, so it can't be true that m is positive. Of course, it's 0 on the boundary, so that m is less than or equal to 0. And so it's got to be less than or equal to. It's got to be equal to 0, because it's 0 on the boundary, and that's the max. Can't be positive. So that's the proof. And this leads to a really simple proof of the Schwartz reflection principle for harmonic functions. And that's why I do it. If you look in certain books, you can make a lot of work out of the Schwartz reflection principle. If you want to. But if you do this first, then it turns out to be a snap. So here's what it is. Let's suppose u is a real valued harmonic function on D plus. So the picture is going to be like we had when we did the analytic function. I'll have a disk. Here's the real line going through the disk. Here's the D plus. This whole disk is D. And this D plus thing is here, and the D minus side is on the bottom. And let's see, if I have a Z right here, I would have a Z bar reflected like that. That's the picture. So it's a real valued harmonic function on D plus that is continuous up to R. let's see, I guess I mean by R intersect D, the whole disk, and it vanishes on that part. It needs to vanish there on the real line. Then it reflects as a harmonic function. Let's see what I mean by reflection. Then capital U of Z, which is equal to the given function on D plus. Okay. We know it's got to be 0 on the real line. But then what should it be on the negative side? And it turns out it needs to be not U of Z bar, but minus U of Z bar. Then the fact is that thing you get by reflection is harmonic on the whole thing. It's harmonic on D. Well, I'm not going to have time to prove it. Well, it's easy. And you can show that this capital U satisfies the weak averaging property. So have 2 minutes to... I'm not going to give the whole proof here, so I want you to go home and think about it. But if I gave you this picture here... Here's the picture. The proof would be, think about the weak averaging property. If I give you a spot right here, I can do the weak averaging property because U is harmonic there. If I give you a spot here, I could put a big one in there because U is harmonic. So I can do the averaging property at points like that. And this U of minus U of Z bar, you do the chain rule. The Laplacian of minus U of X comma minus Y is harmonic. That's an easy thing to check by the chain rule. Okay, and so it's harmonic on the D minus. That means I can put in a little disk here, big disk here, little disk in this, little tiny disk in this corner. And so I've checked the weak averaging property almost everywhere except on the red real line. And how would you do it there? The function, so I got to pick I need a weird color. This spot, it's 0 there. And it's minus what it is on the lower half disk than the right upper half disk. So the averaging property holds at the green dot too. So the weak averaging property holds at the green dot because it's minus on the top what it is on the bottom, or vice versa. So I did manage to